Last time we looked at a block being pulled by a force that acted up at an angle. This time we're going to change that up a little bit. And instead of letting the forces act at an angle, we're going to put the block on an incline. And this changes a couple things, because before we still had acceleration only in one dimension. We had it accelerating horizontally. But now this thing is going to accelerate down the incline. And we're going to assume a frictionless case for now, but that means this thing will accelerate this way. Well, this is my acceleration vector. That acceleration vector has an acceleration in the x direction and an acceleration in the y direction. Now this angle right here is the angle theta. This triangle is symmetric to that, so this triangle is also got the angle theta in it, which means if I'm keeping track of this, the acceleration in x is really the acceleration of the block times the cosine of theta, and the acceleration in y is equal to the acceleration times the negative sine of theta. Now where did that negative come from? Well, this acceleration is down, and I'm assigning down as negative. So a sine negative theta, or a negative sine theta, gets me the acceleration in y. Now there are a couple forces that act on that block, and I did say we were going to ignore friction in this case, so I've got the force due to gravity, which is pulling this way, Fg, and I've got the normal force, which remember has to be perpendicular to the surface. Now let's be careful with that. This force is all in the y direction, so it doesn't have another component, but the normal force is pulling up and right, which means it has two components. It's got the force vertical, Fny, and it's got the force horizontal, Fnx. Now if we look at this triangle, we can actually show using geometry that this angle theta is the same as this angle right here on that triangle. I'm not going to go through that derivation right now. If you'd like to see it, let me know and we can do it. But this angle and this angle are the same, which means Fnx is equal to the opposite side, so that would be Fn sine theta, and Fny is the adjacent side of that triangle, which is Fn cosine theta. Okay, so now I have a way to describe the acceleration in x and y, have an accelerator, and the forces in x and y. So let's apply Newton's second law to this thing and see if we can actually find the acceleration of the crate down the incline. So we have to keep in two dimensions because we have forces in two dimensions and acceleration in two dimensions. So the net force in y is equal to the normal force in y, Fny, plus the force due to gravity, Fg, and that's equal to mass times the acceleration in the y direction. Now we've got to do the same thing in x. In x we have the net force in x is equal to Fnx, and that is equal to the mass times the acceleration in the x direction. So I have two equations, one with Fny and Fg and Ma, and this one, May, with Fnx and Max. So I've got a few unknowns running around, and I'm going to go ahead and start substituting these values in so that I can have these two equations talk to each other, because now they have x and y values in them, and if I can get rid of the x's and y's, then Fny and Fnx become Fn, and I can combine those. So Fny I'm going to replace with Fn cosine theta. Fg, I'm actually going to replace with m times negative g. Again, where did that negative come from? Well, Fg is equal to mass times the acceleration due to gravity, and since I assigned down as negative, the g is negative, equals mass times the acceleration in y, but the acceleration in y is really a times the negative, so I'm going to put that negative out front, sine theta. Okay, so now let's see if we can simplify this a little bit and solve for let's solve for Fn. So Fn is actually equal to, I can add that mg over, mg plus a negative ma sine theta, and I've got to divide everything by cosine theta. Cosine theta, cosine theta. Alright, so now I have an expression for Fn, and it looks complicated and messy, and that's mostly because it is, but we can go ahead and substitute this equation in for Fn over here, except I don't have Fn over here, I have Fnx. So let's make a substitution here. Fnx is really Fn sine theta. So Fn sine theta is equal to mass times the acceleration in x, and let's get rid of the acceleration in x and just make it acceleration cosine theta, right? So I made this substitution for this equation, and now I'm going to put this in for Fn, and so I get mg sine theta over cosine theta, because I replaced I multiplied this term by sine theta, minus ma sine theta squared, sine times sine is sine squared, over cosine theta, equals ma cosine theta. Okay, so now I've just taken this equation for Fn and I've substituted it into this equation for Fn. Now I've got to simplify. So I don't like that cosine theta is at the bottom of this term, so I'm going to multiply everything by the cosine of theta. That gets me mg sine theta minus ma sine square theta equals ma cosine square theta. Right? So I multiply this term by cosine, the cosines drop out. I multiply this term by cosine, cosine drops out. What I do to one side, I have to do to the other, so that gets me cosine squared. Now I can add over ma sine squared theta, get mg sine theta is equal to ma, and I'm going to go ahead and factor that ma out, sine square theta plus cosine square theta. Well, that's a Pythagorean identity. Sine squared theta plus cosine squared theta is 1, which means mg sine theta is equal to ma. Mass is on both sides, it cancels. G sine theta is equal to the acceleration. That is a very nice, simple representation for the acceleration that went through a big, long derivation. And we can actually get there a whole lot faster if we do something tricky at the beginning. Okay, at the beginning, I just let x be positive x and y be positive y, and those were at right angles to each other. And they always have to be at right angles to each other, but they don't always have to be horizontal and vertical. If I rotate that so that the x is along the incline and the y is perpendicular to the incline, that changes some things. So let's see what that changes. The first thing that happens is if I rotate my frame of reference from being horizontal and vertical to rotate it at this angle, then the acceleration in x and y doesn't matter because there is only acceleration in x. This is my ax, and there is no acceleration in y. So this whole thing goes away, and so the acceleration in y is equal to 0 because it's only accelerating along the incline, so the acceleration in x is the acceleration. So that's different. These two things have gone away. And when my acceleration in y is 0, that's going to make dealing with the forces in the y direction easier too. And so let's think about y. Now that I've rotated my frame of reference, the normal force is actually parallel to my y-axis, which means this force right here doesn't need to be here, and this vector doesn't need to be there either, because all of Fn is actually in the y direction, which means I'm going to have no components for the normal force. However, gravity now does have components, because some of gravity is straight down and I don't have an x or y straight down, so I've got to draw in my components. Okay, remember x and y are at right angles to each other, so this is actually FGX and this is FGY. So now the normal force, instead of considering the normal force as being the force that is causing it to move right and gravity the force that's making it move down, we're letting the components of gravity act, and so the component of gravity, Fgx, is going to be the thing that causes the acceleration. And so we have to figure out what that is. And just like before, this angle here was theta, this angle here is also theta. Vertical angles are congruent. And so what we can do is we can apply Newton's second law in both directions. Okay? So Fgy, if we look at that, is equal to Fg, the force due to gravity, and that's adjacent to my angle, cosine theta. And Fgx, that's opposite of that angle, is equal to Fg sine theta. Okay, so now let's go to the net force in x and y. So the net force in x is equal to Fgx, which is equal to ma. Right? Because the only acceleration is the acceleration in x, and so that's our acceleration. And the net force in y is equal to Fg sine theta, FGY, we'll go with that, we won't put it in yet, plus Fn, and that is equal to 0. Right? So now I've got these two simple equations, and since this acceleration is 0, the net force is 0. And so I can say Fn is equal to the opposite of Fgy, and since Fg is mg, this is Fn, but again g will be negative because it's down, is equal to negative m, negative g, and y becomes cosine theta. And so what I get is the normal force is equal to mg cosine theta. Okay? Which would be handy if there was friction and I knew the coefficient and wanted to find the frictional force. Now I have this cute little expression for the normal force. We still don't have an expression for the acceleration of the block without friction acting on it, so let's go back to our net force in x, and we'll have net force in x is Fgx, which is going to be mg sine theta, right, equals ma. And m is on both sides, and so g sine theta is equal to the acceleration of the block, assuming that the only forces acting on it in the x direction is gravity and there is no friction, right? So this was much simpler because we rotated our frame of reference to be parallel to the acceleration instead of having components of acceleration.